To the first of our C++ lectures. In this series, we're going to have a look at C++ as a programming language in terms of how we can write code within it, but also importantly in terms of how the code that we write in C++ gets to be executed. We're not going to look at C++ from the ground up. Instead, I'm assuming that you're going to be reasonably comfortable with a language like Java or C#. So a lot of the content here will be a compare and contrast between the two. There's two main reasons why we want to do this. The first one, arguably sort of the minor reason, is that it's useful to know more programming languages, because then you get a better understanding of how do they differ. And if you're given a problem, you can ask, well, what is the right language, the best language for solving this problem? The second reason, and from the context of this, the more important reason, is that C++ is a fairly low-level language. It will put us in a situation where it's going to be important to understand how the code that we write in C++ gets to be executed. So we will have a better appreciation of how code runs. And if we know this in C++, exactly the same principles will apply to Java, to C#, to other languages. So in a very, very real sense, in learning C++, we will become better Java, better C# programmers. And I want to make use of this initial lecture to try to make that argument, to justify why I think that is the case. So we're going to look at why C++ is, I'm saying here, awesome, but awesome in a somewhat painful way. And the old adage of no pain, no gain, I'm afraid most certainly does apply to C++. We will become better programmers. I'm afraid there's likely to be pain associated with doing that, but it is genuinely worthwhile. But I have a little bit of context, and I think context is important here in terms of understanding where C++ came from, because this will help us better appreciate why the language is the way that it is. It's an old language. It was originally created in 1982, and on the next slide we have a timeline where you actually can see the things that it came from. And as a language has a different approaches. Generally speaking, when you put in a language, it evolves and changes over time. You get new features that come in. Languages like Java and C#, if you got a new feature that comes in that replaces an old feature, say does it in a better way, those languages will basically deprecate the old approaches and will say, don't do it, use the new approach. So they are willing to basically rule out old approaches. C++, they never did that. There was a very strong need to maintain backwards compatibility. So if you had a language that's evolved over 30, 40 years, which has been adding in new features, but hasn't been throwing things out, that adds to one of the complexities of C++. It's a slightly messy language. You can see how it has evolved and how it has changed over time. Back in the 1980s, in fact, let's actually go back a little bit prior to that, to the 1970s. If we go back to the 1970s, you see a timeline at the bottom here from 69 up till 2001. And it shows a number of programming languages. Some you will have heard of, some you probably will not have heard of. And it illustrates when they came in and what other languages were influenced, where they were derived from. So 1983, actually, we have C++. That's sort of down towards the middle of the chart at the bottom. And you can see that C++ actually was derived from C with classes. And if you drop the line down and then go back over to 1971, you can see over there we have the C programming language. So C++ really is a superset of C. C is a procedural language. C++ basically added in object-oriented elements on top of C. Back in the 1970s, computers were millions and millions of times slower than they are nowadays. And everything had to be, well, it wasn't as complicated as it was now. Things were fairly bare and basic. Certainly everything had to be as fast and efficient as it possibly could be. So C, as a language, is fairly low level. It gives you a lot of control, but it has no safeguards, no checks built into it. And C++ inherited those particular components. So in C++, most C programmers if they write a line in C, they can have a fairly good understanding of the types of assembly instructions that would be turned into. C is still very broadly used today. If you're doing embedded programming, almost certainly it'll be in C. And so in terms of things that down at the device driver level where you're talking to hardware. C, to be fast, doesn't have a lot of error checking built into it. So by error checking, we mean things like if I create an array of tenants and I then try to access position -2 or position 314. Now, it seems silly because we're accessing a position which definitely cannot be an array of tenants. And if you try to do that in Java or C#, it would go, no, you can't do that. That's just a silly error. In C, if you ask it to do that, it will do it. It won't throw up its hands. It won't check to see has the programmer done anything silly. It will just simply do whatever you ask it to do. So there is very, very limited error checking built into it. That makes it run faster because you don't have this overhead. But it also means that the programmer has to be very careful about the code that they write. And if you do put in an error, it's going to crash, probably in an unpredictable way. We then have to go through and to work out, well, what it is and then to fix it ourselves. So that's a characteristic of C and indeed C++, that the language gives you a lot of control. It will do whatever you tell it to do. And that's where the control comes from. But if you tell it to do something silly, it will do something silly. And it won't worry about it. It's then your problem to find that and to fix that. What does that mean as a consequence? Well, if we are writing code in C++, we have to be more careful about the code that we write than we would be if we're writing it in Java or C#. So it demands more care and more attention, because if we don't put in that care and attention, we're more likely to put in bugs which will cause the thing to crash, which won't be picked up and detected because we don't have much of the error checking built into it. So that's a painful aspect. It's a hassly aspect. It's ideally something we don't want in a programming language. To minimize the probability of us introducing bugs into your C++ code, and you will want to do this because if there is a bug, the programming language isn't going to really help you find it. You're going to have to go through and work it out yourself. And that is actually painful. So there's an encouragement to write the right code in the first place. And for us to write the right code, what it means is that we will have to have a good understanding, a very good understanding of the code that we write down. That if we write this, what exactly will that do? And we're not inadvertently putting in bugs or doing something silly. And this requirement, so to speak, for us to have a better understanding, a more precise understanding of the code that we write, that's the thing that's useful. It's going to make us a better programmer overall. C++, there's been a number of evolutions. You can see 3 of them here. There's really only the one on the left and the one on the right we're interested in. So back in 1998, you had ANSI and ISO, or standards organizations. They produced a publication for C++ 98. You can think of that as traditional old style C++. They standardized it because then you could have different compiler writers that could adhere to this standard, and you could then have one person write code that could be compiled across multiple compilers. 2003, there was a small technical correction, doesn't really matter. C++ in 11, which was in 2011, this was on the right hand side, this was a major revision to C++. And then it actually updated C++ to include a lot of the features that you have within Java and C#. So if you think back to the timeline, both Java and C# were influenced by C++. When they were created, they drew upon C++ in terms of their syntax, their structure, things like that. And here we have a situation where in 2011 you have C++ itself drawing upon those languages to evolve, to update itself. So what came in C++ 11 compared to C++ 98? I've got a few of the things here. Now, at this point, it's not going to make a huge amount of sense. Whenever we've gone through and looked at them, it probably will make more sense. But at a high level view, the key difference is that C++ 11 introduces techniques that are less dangerous, that avoid some of the more dangerous techniques that C++98 has, and is drawn upon solutions and forms that you use within Java and C#. So I'll give you a few examples. For example, smart pointers instead of raw pointers. C++98 has pointers. You point to an address in memory. And in C++98, a raw pointer is just simply an address in memory. You point to a location in memory and nothing else. A smart pointer does more than that. It points to an address, but it also knows the type of thing that it points to. And that's useful if you're then accessing something through that pointer, or you're dealing if it does something still refer to it, or things like that. Stack-based scope instead of heap or static global scope. You'll see when we look at C++ that when we create an item of data, a variable, an array, whatever, we can have a good degree of control over where it gets to be stored in memory. We can position it wherever we want to position it. And sometimes we can position it in per locations. In Java and C#, these are managed languages. So when we create an object, we don't get to choose where it gets to be created in memory. It's managed for us. We only deal with it indirectly through a reference. And so on and so forth. So other things here about using containers instead of raw arrays, about auto-tight inferences, about robust looping instead of unsafe looping. They're all features that Java and C# have that have migrated into C++ as good practice. Now, this said, if you were actually going to write a project in C++, I would strongly encourage you to use C++11. It's modern C++. It's the one you should use. It is better than C++98. But in this course, I'll cover some aspects in C++11. I mostly want to look at C++98, old style, traditional, unsafe C++. And there's a couple of reasons why I want to go with old style C++. I'll try to set it out here. So I've said earlier on that C++ and C, they are fast languages, and in terms of if you read around, you'll see that generally if you want to write something that has to be high performance, C, C++, these are the languages that are suggested. It's also a relatively difficult language. Three main reasons why it's fast, and you can see them here. It provides the programmer with a low-level programming features and lots of control over how the code is executed. So you can access things at a very low level of detail. I can get down level of memory and modify things and such not. It mostly avoids runtime checks, assuming that the programmer will have written correct code. So there's not a lot of overhead within it that double checks I'm doing something safe and double checks that and checks this. It basically is trim. If I ask it to do something, it'll do it. It's up to me to make sure it's doing something right. It's a compiled language and has many excellent optimizing compilers. Another talk, we'll have a look at interpreters, just-in-time compilers, full compilers, things like that. C++ is fully compiled, and there's a number of rather excellent compilers that will go out of their way to produce highly optimized code that will help us write code that runs faster. So these are the things that make it fast. The main thing that makes it difficult was the middle item, that it avoids runtime checks. Now, let me take a step back. I said C++ is a language that lets you write fast code. Just because it lets you write fast code, it doesn't actually mean that I am more likely to write fast code. It's up to me to write the code. If I do it correctly, this will be able to run it fast. I can quite happily come along to C++ and to write a piece of code that is inefficient, and I will never be able to run it fast because I've written it in an inefficient way. But there is a feature in C++ that helps us, or makes it more likely, that we will be writing efficient code. And it comes into the bit we have here about avoiding runtime checks. In C++, we will have to be more careful about the code that we write. We will have to be more sure that yes, it is doing exactly what we want it to do. We're going to have to understand on a deeper level the code that we say, what it actually will do. Now, if we do this, it means we can write safer code that is going to do what we want it to do. But by having that understanding, it also means that we will be less likely to write inefficient code. It's very, very easy, and I see this very commonly in Java and C#, where because it's a managed language where you don't have to worry about objects being allocated and deallocated, programmers take it for granted. They allocate a whole bunch of objects which are then very quickly deallocated. From their point of view, it just happens. But something has to do it, and under the surface you have the virtual machine spending a lot of time and effort doing this. Basically, it's inefficient. So C++ will give us the right level of understanding that will enable us to write code then that will be fundamentally more efficient, be it in C++ or Java or C#. So that's the main advantage that we will get out by looking at old style C++ and looking more precisely at how things actually get to be executed. So main advantage of C++ 11 is that there's less sort of mundane tasks for the programmer. There's a number of things that deal more with automatic housekeeping. So C++ 11 is very much more like Java and C#, and you could more or less write equivalent things within it. That's good, and you're writing things, that's brilliant, but not from a learning point of view. As mentioned here, we do want to understand things at a lower level. Now, do you agree with me? Do you disagree with me? Let me show an example to try to make a point in case here. So here I have a fragment of code. Now, it happens to be in C++, but you can look at it and I think it almost be Java or C#. Syntactically all similar. All it does is it adds up the sum of values within a n by n sized array. So in size line 1, we're defining n to be 5,000. So the array called A contains 25 million entries. And we're going to, in lines 4 to 6, step across those entries, add them up into a sum. So you can see in line 4, we're saying x equals 0, less than n. Line 5, y is equal to 0, less than n. So we're simply going over x and y. And in line 6, we're assuming we have a sum variable, let's say initialized to 0. We are adding on the array entry to that. So it's x plus y times n. So basically, x is the outer loop, y is the inner. So here we are adding this up by each of our column. Column after column after column, we'll add them together and then sort of step that across the full row. And we'll get our answer at the end. I timed this in a particular processor. Took 240 milliseconds to complete. So let's assume that you have to optimize it to make it run faster. Here's a version that will run faster. So in this particular case here, fragment took 80 milliseconds. It runs roughly 300% faster, 3 times faster. That's a lot faster. So what magic did we work to get it to run 3 times faster? So n still 5,000. We still have an array. I assume it's exactly the same data in both of these arrays. The only change we've made is we've swapped lines 4 and 5 about. So as opposed to x being the outer loop, it's now the inner loop. And y, as opposed to the inner loop, it's now the outer loop. So 4 and 5 swapped around. Line 6, we work out exactly the same sum. So here we are calculating the sum row by row by row down through the n by n matrix. One's 300% faster than the other. And it doesn't matter if you wrote this in C++ or Java or C#, depending on the size of the array and the processor you're running on, you'll get something similar in terms of a significant performance difference. What this hopefully illustrates is that it is easy to write 2 fragments of code that, at a high level, functionally look to do the same thing. But in terms of how they actually get to be executed, they can be worlds apart. And if we want to write code that is fast and is efficient, it is actually important to understand in these 2 cases what will happen under the surface. How will they get to be executed? Why is one likely to be faster than the other? And we will be having a look within this about aspects about how data is set out in memory, about how it's accessed, and that understanding would actually be sufficient to enable us to understand, yes, it's better to implement it this way as opposed to that way. Now, old school C++, it's going to give us that right level of access to see this. So key takeaways in this, C++, it is actually a nice language. It can be a very pure language. It certainly is quite a challenging language, but it's a good one to look at. We are looking at C++ on this particular course because we want to understand how code gets to be executed down a level. And we're doing that not only for the benefit of writing good quality C++ code, but because we want to write better Java, C#, any other language.